So we left off looking at examples where we were looking at the difference in population proportions. But before we kind of dive back into that, you've got that current Connect assignment there. We won't do Excel work for the two population stuff until we get till Monday. So we should be able to cover the third example today. And then we'll do some Excel work on Monday, and I'll post the next Excel assignment then. I also put down here kind of your raw exam scores are now kind of in the category. They're not kind of influencing the grade at all. But I've identified which of those was your highest and your second highest exam, kind of weighted those according to the syllabus. Like I mentioned, your lowest exam would be only 15%. So this could change a lot depending on what you get in the final. Right now, it's just kind of like thinking that these first two exams are going to be your best. So if you didn't do too well on one, this is kind of like a worst case scenario if you don't do better on the final. Okay. Other than that, any questions from you before we dive into things today? So if you didn't get your exam back, I do have them here today. I can give them to you after class. And I want to make sure that once we get there, I have this pulled up because I just remembered that I did not open it before we started going. So we're talking about the difference in population proportion or sample proportions, and we already done some confidence intervals. What we're going to do today is look at how do you do hypothesis testing when we have examples like that, and then we'll move on to situations where we've got sample means, but we don't only have the sample variance. So the steps literally are going to look exactly like what we were doing before for even a one population example. We'll figure out what the normal alternative hypothesis are. We need to know what level of alpha we're going to do. We can do multiple levels of alpha. We can find our critical values, test statistics, p-values. All of it's going to be the exact same way. We're just going to have a slightly different test statistic. Just going to go back here, which where is it? I know I looked at it. I showed you guys last class, or at least wrote it up on the board. Let's see. There we go. All right, and we said we're going to have to do kind of this weighted average of our two sample proportions, kind of p-bar. Then we can plug that in, figure out what the standard deviation is of the difference in those proportions. But it's going to follow similar notes. It's really what we're trying to do is the same thing. So I've got this written out a little bit differently, but if we're thinking about the difference in our proportions here, we're going to take the sample evidence we found, right? What was this sample difference? Subtract our assumed true difference. We said we're going to keep this as 0, and then divide by the standard deviation for the difference in those two proportions with the assumed true difference of 0, right? So that proportion is going to be based, or the standard deviation is going to be based off of what the true population proportion is. We don't know what that is, so our kind of best estimate is weighted average. So with that in mind, let's go to this example, right? So let's say I go back to the last election, and I had this polling data. So we did a phone poll with 1,500 people, so a really large sample size. We had 49% of people planning to vote for Biden, 47% for Trump, and we wanted to say, okay, I'm going to test for whether or not Biden is going to receive more votes than Trump in the upcoming election. So if I think about defining this as portion of Biden voters minus portion of Trump voters, if I want to test for whether or not Biden is going to get a higher proportion of the votes, what am I thinking this difference is going to be? Positive, right? So that's what I want to test for. That's going to be my alternative hypothesis. The way we typically write this is just whatever the true difference is. So sometimes, even though we write the null alternative hypothesis with this capital D, like this difference, if it helps, you can kind of write out what that difference is, just so you can kind of think about, oh yeah, if Biden gets more, this would be positive, less negative, or if they're different from each other, not equal to. So we then assume the exact opposite is true, that difference is less than or equal to 0. So if I look at my alternative hypothesis here, I have what type of tail test? I have a greater than sign, so I have a greater than or a right tail test, right? Only evidence I'm thinking about that distribution for the difference in my sample proportions. I've assumed the true difference is 0. If I'm wanting to test for whether or not it's greater than 0, only evidence on the right-hand side would go against my null, right? Evidence on the left-hand side actually supports it, okay? So I look at this and I say, well, I've got a sample proportion of 0.49 for Biden, 0.47 for Trump. So the sample difference I found was 0.02. Okay? So it's evidence on the right-hand side, but is it strong enough evidence? Right? Well, what we're going to have to do to figure that out, we could do two approaches. One, could figure out what the area to the right is for a right-tailed test. That would represent our p-value, the probability we saw sample evidence as far away from that assumed true value as we did, or anything further. So we could turn this into a test statistic, find that p-value, compare it to alpha. Or we could figure out what's the critical value, and I don't know, I might be drawing this wrong because I don't remember this one off the top of my head, but it could be here, it could be here, but whatever critical value I find, I want the critical value that gives me an alpha total in the tail. So we'll kind of use both approaches. I'll do the p-value approach first, and then we'll do the critical value approach. So the p-value approach, the first thing we're going to need, skip this for a second, there we go, is our test statistic. This is just going to be a matter of plugging everything into our equation. So if I write in, I'm knocking everything off here. We had p bar times 1 minus p bar times 1 over each sample size added together. Right? So I'm gonna erase it. Oh, it's not. So let's just write this out. Right? I've got 0.49 as my proportion for my first group, or the proportion of votes Biden get. 0.47 for my second group, the proportion of votes that Trump's going to get. I've got this assumed true difference of, I might just write that number in, 0. Now here, remember, P bar was going to be this. We're just kind of finding this weighted average of the two proportions. So here it's kind of easy because we have the same sample size for both groups. So I'll do 1,500 times 0.49 plus 1,500 times 0.47 divided by the sum of the two sample sizes. Well, if I'm doing a weighted average and my sample sizes are the same, then it's just going to be the middle value in between those two sample proportions. So you can get this entered into your calculator. What you'll find is this is basically just going to be the middle value between 0.49 and 0.47, right? It's the weighted average, but if the sample sizes are the same, it's the number that's exactly in the middle. So here our P bar should be 0.48. We'll then multiply that by 1 over each group's sample size. Now it's just a matter of getting this entered into our calculator. So I would probably break this down into steps. I would probably try to figure out what's inside of this square root first. Once I have that, or that one number, I'll take the square root of it and then have just one number in my denominator. I would just, you can do it all at once, but breaking it down into parts is going to make it a little bit easier in your calculator probably. If I look at these test statistics, hopefully we're kind of getting an idea about what they should look like. Which of these seems really unlikely? Yeah, why? I mean, 42 standard deviations away. I mean, once we get to 2 or 3 standard deviations, that's pretty far, right? 42 standard deviations away would be like if we saw a sample difference of, I don't know, 0.78 or some really, really big gap in between the two proportions. Here we've only got a 0.02 gap. Probably that the number of standard deviations away we are is not going to be that extreme. So if we actually just go ahead, plug everything in, we get 1.097. So my test statistic that we found, 1.097. If I want to find the p-value or the area to the right, I can use my standard normal table. So I will go to that z table. Now I can only go to the second decimal, so 1.097 would round to what? 1.1 actually. So, or sorry, 1.0, yeah, 1.1. So we scroll down 1.10, so 0.8643 is going to be the area to the left. That's not my p-value, right? If it helps to just kind of remember, p-values are generally going to be less than 0.5, right? If we found sample evidence on the right side, right, that goes against the null, well, that p-value should be less than 0.5, right? Because 0.5 is the area to the left and the right of that assumed true difference. So we know right away 0.86 doesn't make sense for our p-value. What did I forget to do? Well, if I want the area to the right, I just do 1 minus that. Okay. So write this over here. I'll leave this up just for, I think, for the next example. No, I shouldn't erase that. So we've got a p-value of 0.1357, I think. I reject the null if that p-value, the probability I saw, the sample evidence I did, is less than that threshold alpha probability that I set. And kind of think about alpha is just like, if the probability falls below this, I'm okay rejecting the null, right? So is that value less than 0.1? No, so I fail to reject the null at the 10% significance levels. It's not less than 0.1, it's not going to be less than 0.05 or 0.01. So here's a situation where I fail to reject the null at every single level, right? So if I was trying to predict this selection, remember what I was trying to test for was that that difference was greater than 0. So I assumed it was less than or equal to, right? So that the difference between Biden and Trump was either they're exactly the same or Trump was actually going to get more. I couldn't actually reject that null, right? Now I found sample evidence that suggested that Biden was going to get more votes, but I couldn't say that at 90, 95, or 99% confidence levels. Now, that being said, and this is a good thing to point out, just because I can't say it at my benchmark, you know, what levels could I say that? Well, if I think about the 85% confidence level, what would my alpha be? So alpha is the percent outside in decimal form. Yeah, 0.15. So at the 85% level, I could have rejected that null. And I could have said, yeah, I'm going to reject that difference is going to be less than or equal to 0. Or I found evidence that supports the difference is positive, or that Biden is going to receive more votes. So just because we can't set the benchmark levels, you know, in practice, doesn't mean like we have completely worthless evidence, right? Pretty close. Now, sorry, before I keep going, any questions kind of anything we've done up to this point before I keep moving? Okay. So what if I wanted to find, and I forget what level we had here now. Let's go back here. So let's say I wanted to do this test at the 99% level. I want to find the critical value, and I kind of know where this is at so I can cheat. Usually it makes more sense to find the critical value first and then plot your test statistic against it. In fact, let's just redo this and I can kind of show what that looks like. So let's say I'm wanting to find this critical value that gives me this alpha of 0.01, right? My 1% significance level in the tail. Okay? Well, there's two ways I can do, or actually 3 ways I can do this, right? For a right-tailed test, I can look up that alpha of 0.01. However, if I look that up in my z-table, remember the z-table always is giving me the area to the left. So if I look up alpha of 0.01, I'll find the value that I need, that number of standard deviations, that's my kind of threshold cutoff number of standard deviations, but it's going to be that value but negative. So I can look up alpha and just remember, it's a right-tailed test, it's going to be that value but positive. Or I could look up the area to the left, which would be what here? Yeah, just 1 minus that, so 0.99, right? So let's see what that looks like. So I can do it one of 2 ways, right? I could look up 0.99, which looks like I'm in between these two right here. So 2.32 and 2.33. So 2.33. Or I could have looked up that area of 0.01, just my alpha value. So I look up 0.01 here. Looks like I'm in between these two. So negative 2.32 and negative 2.33. Oh yeah, that's the number of standard deviations I want. But if I'm looking at the left side, I'm actually have a right tail test, so it will be that value but positive. So you can look it up either way, whichever way kind of makes sense to you.
This one where you can use a t-table too.
You always can, right? You can use it to cheat, right? Not cheat, but the shortcut, right? So here I wanted what? 0.01 in my tail. I could have also went to my t-table, looked up that area I wanted in the tail, and remember the last row with the degrees of freedom of infinity, that would just be that the student t distribution converged to the standard norm. So I could look at that last row and see, oh yeah, 2.3. I don't even have to go to the second decimal. I can go out to the third decimal. I can be a little more precise. Any questions over any one of those ways of kind of looking up that? Is that hopefully starting to, we're really doing the same thing, like, you know, it's just, we've got a different test statistic equation. That's really the only thing that's changed. Okay. So once I have my critical value, for a right-tailed test, my rejection region is the area to the right. So if I plot my test statistic and it's in that rejection region, I can reject. If not, I fail to reject. Well, my test statistic, if we remember, was 1.097. So I'm not really close to that 99% confidence level rejection region, right? I can't reject at that 99% level. Okay. Any other questions on this example? I'll move to the next one. So hopefully it's like, I don't know, we can start to see. So I think I have all this, right? Oops, where we're comparing this. Hopefully we can see, like, we can start to make predictions. Like, this is exactly how they do kind of like election predictions. You look at the polling data, do this hypothesis test to see, like, is this candidate going to get more votes? Essentially set up the exact same way that we just did. And you can see, you know, at what levels can I predict that this candidate's going to win this election, right? So when they start doing a little bit more complicated because there's different like demographics in the states, but when they start getting a certain percent of the vote in, what they're really doing when they, like, if you ever watch election stuff, which you probably have better things to do than that, but they'll be like, oh, we can predict this with this percent level of confidence. That's really what they're doing. They're looking at what the current votes are, the current sample size is. You know, we're talking about sample size of 1,500 here. When you're looking at actual votes, we're getting sample sizes in the millions sometimes. You know, if we're getting sample sizes in the millions, if I increase my sample sizes here, that's going to drive this to be lower. So if this is lower, my test statistic gets higher, pushes it way out here, I can start to be more accurate in my predictions. So once we start to get a lot more of the vote in, you can look at what the current proportions of voters are and say, well, we can predict it with this level of confidence. And like I said, it gets a little bit more complicated because, like, depending on if, you know, certain precincts have reported and other ones haven't, but as long as we kind of assume that every precinct is kind of reporting at the same rate, we could do exactly this and kind of make those real life or real time projections. So go through another example, and I think I'll ask this because I want to see kind of where you guys are at with this, because I know the exam is a little bit tougher for people, so I want to see if we're starting to get kind of the hang of this hypothesis stuff. So let's say we've got this 2010-2011 survey, and we want to know what's the difference in views of healthcare coverage for everyone. So I've got 84% in 2011, 82% in 2010, and I want to test the proposition that Indiana residents have different views between the 2 years. So if I'm wanting to know, is this sample proportion from both of these time periods, basically, are they different from each other? Right? So if I think about the difference between 2011 and 2010, if I want to know, are these two proportions different from each other, what would that null and alternative hypothesis look like? It's going to be a little bit of time to think about it. So sometimes it helps to write out what that actual difference is. So if I want to know, are these two proportions different from each other? Thinking about what is going to be true. What am I trying to test for? Right, that difference is going to be something, what, greater than, not equal to a certain value. All right, you haven't gotten the answer in. Now take your best guess here. Yes, a little bit more time. Okay, everybody got, we got 27 of us here today. So let's take a peek. All right, so got some confusion here. If I'm wanting to test for whether or not these views are different from each other, what I'm really saying is the sample proportion in 2011 not equal to the sample proportion in 2010? So anytime we see this term different than, it's the same as a one population test. We said this terminology of different than should tell us if it's not equal to sign that in an alternate hypothesis. So right away, we should be ruling out A. Excuse me, from there, we need to kind of write this out as, well, what's the difference, right? Well, if I try to subtract this from both sides, I'll end up with that I want to know, is that difference not equal to, that cancels out, 0. If I'm saying, are these proportions different from each other? That means if I take one and subtract the other, I'm going to get some value other than 0, or a value that is not equal to 0. Okay. So anytime you see this term of different than, right, we should be thinking not equal to sign in my alternative hypothesis. Also, I already told you, I mean, I guess I could have reiterated it before we went to this. But what did I tell you? I'm always going to use the assumed true difference of 0, right? So right away, we should, be thinking about, okay, I really could limit this down to 2 options. And then I see this terminology of different, and hopefully that helps me identify kind of this not equal to, right? But, it's not just in those terminology. You can think about, really, this is what we're trying to do. Is this time period's proportion of views of healthcare different from or not equal to this other time period? Okay. So we've got a two-tailed test, right? What are my critical values going to be? So get rid of this here and think about, the black marker's dying on me. What are my critical value or values going to be? Well, I've already kind of let you know that we're going to have a pair of critical values. Right? We've got a two-tailed test. So that means we're going to try to figure out the number of standard deviations away we need to go to get alpha total in the tails. This is where we said two-tailed tests look really similar to confidence intervals, right? When we're looking up that z-value for confidence intervals. So if I've got an alpha total of what, 0.01 in my tails, how much is in each tail? Well, there's half of alpha in each tail. So 0.005. Yeah. So I've got 0.005 in that tail, like area in the tail. That's what I want. And I want to find what's the number of standard deviations, or what's that z-value? How many standard deviations away do I need to go to get that desired area in the tail? So once again, I could just look up in my z table, what, 0.005. I might have said 0.01 before, sorry. 0.01 is the total area in the tails for our two-tailed test. Divide that by 2.005. So we scroll down, looks like we're in between these two values. So negative 2.57, negative 2.58. So that's going to be kind of one of our critical values. Our other one is going to be that same value, but positive. All right, so I said the way that we typically write this kind of identifying, we have two critical values, the same value, but one's positive, one's negative. Okay. Questions on that idea? Now, what could I have also done there? A little bit of a shortcut. Just like before, I could have used that t-table, looked up that area of 0.005, and remembered this last row would be the z-value that would give me that desired area in the tail. So I don't even have to be constrained to kind of 2 decimals. I can be a little bit more precise. Okay. Now that I've got these critical values, the rejection region is going to be anything that's more standard deviations away than these cutoff values, these critical values I just looked up. So what are going to be, for a two-tailed test, the area to the right of the positive value, area to the left of the negative value. So the next step is, well, what sample evidence did I find, right? And whatever that sample evidence is, I need to turn it into a test statistic. So if you think about what we're doing here, get rid of it. We've assumed that difference is 0. I found sample evidence, right? 2010, or sorry, 2011, it was what? 0.84. 2010, it was 0.82. So that sample difference is 0.02. So I found this sample evidence of 0.02. I'll turn it into a test statistic. I could then figure out what's the area to the right if I wanted, no, what I, in practice, sorry, I'm jumping ahead. I found this sample evidence of 0.02. If I turn that into a test statistic, I can plot that and see if it's in my rejection regions. If I want to do the p-value approach, I would turn that into a test statistic, find the area to the right, and then remember for a two-tailed test, it would have been equally as likely that I saw sample evidence on the other side that now goes against my null, right? Because now evidence on either side goes against it. Okay? So how do I find this test statistic? It's really just a matter of, we're going to have that formula in front of us. It's just a matter of plugging in the values we're getting, or that we calculate from data. We've got our sample proportions. We've got our sample sizes here, 607, 600. Here's our test equation. We said now we have this kind of additional step, which is figure out what this p bar is, or this kind of weighted average. So plugging our sample size, sample portion, we get that weighted average with p bar. We have to plug that in right down here. Sample sizes, sample portions. Assume true difference is always 0, so you can kind of ignore that, right? And this is just a matter of getting probably familiar with using our calculator. Okay. As we're at this point, I will mention as well, I put up the next formula sheet for the final. So these formulas we're going through, if this loads, I don't know if this isn't loading, will all be here. So like you'll have the test statistic equation, like it's just a matter of, it's going to be in front of you, you'll be able to look at it and then just kind of plug in the values for that problem. Well, I guess we'll download it. I don't know why it's not pulling up on the page. So, and if you ever have problems with that, sometimes people contact me. If things don't pull up on Canvas, a lot of times it's just download them and it should be fine. I don't know why it still has some issues with that. But, right, we've got these test statistical equations right here. Okay. I also, as long as we're on Canvas, wanted to point out, I put up the second exam and its answer key as well on Canvas if you want to kind of go back through those. Okay. So we get this test statistic of 0.925. I plot that against my critical values, and I'm nowhere near my rejection region, right? So I failed to reject at what, the 99% confidence level or the 1% significance level here. Okay. Now, the advantage if I had found my p-values, this is why, critical value approach is fine, leads you to the right rejection decision. But I always think the p-value approach is a little bit easier for wanting to do multiple levels. Because if I look at my test statistic here, which is 0.93, I go to my table, I look up 0.93, where's that? 0.93, so 0.8238. But remember, the table always gives me the area to the left. So I forgot what this was, 0.8238. I needed to know what the area to the right was, and then I was going to multiply it by 2. So 1 minus 0.8238, what, 0.1762. Multiply that by 2. I'm going to end up with a p-value that's pretty close to 0.34 if I round it. So I only reject the null if that p-value of 0.32 is going to be less than alpha. Well, here, I only had one alpha, so it was kind of easy when I plot that test statistic against my critical value I'm done. If I had the p-value, I can compare to all 3 levels relatively quickly. Now, once again, I have a situation here where the value is so high, right, that I didn't find strong enough evidence that I can reject at any of my benchmark levels. Questions on this before you keep moving? I'll just show you one other thing I think might be hopefully helpful here. Thought we'd get through a little bit more today, but I'm okay if we don't. So let's say I wanted to use a critical value approach and I wanted to be able to reject at multiple levels simultaneously. What would be kind of an easy way to do that? So visually, let's say we had a two-tailed test. I'd want to be finding the critical values that correspond, and I'll try to use different colors here maybe to make this a little bit easier, to different areas total in my tails. And then so I could find all three pairs of critical values for these three different desired alphas, 0.1, 0.05, 0.01. Okay. I can think about where would my rejection regions be? Well, it's anything more extreme. So to the left of that negative critical value, to the right of that positive critical value, same kind of thing for every single level. So how can I find these values really, really quickly? Well, I know that I don't want alpha total in each tail. I need half of alpha, right? So if I think about for these different alpha levels, what is half of alpha going to be? You write those numbers down here real quick. And then what I could do is instead of hunting down in the Z table, 0.005, find the corresponding Z value, 0.025, find the core. I can do that, but it's really easy. If I use this last row of my student T table, if I want the areas of 0.005, 0.025, and 0.05, I can use these three columns, go to the very last row, 1.645. So positive and negative 1.645 would give me 0.05 in each tail, or a total of 0.1, the alpha I wanted. And then look at the next column of 0.025, 1.96. So that's the Z value that would give me a total of 0.05 in my tails, or 0.025 in each. And then I look at the last column, 0.005 is the area I had in each tail, 2.576, negative 2.576. Those would be the critical values that give me a total of 0.005 in each tail, or 0.01 total in the tails, which was what that alpha I wanted was. Now that I've got these three critical values, let's say I had a test statistic of 1.8, right? Now I can plot that against my critical values and see pretty quickly, okay, I'm in the rejection region at the 10% significance level. I'm not in the rejection region, just barely outside of it at the 5% level, and I'm nowhere close to being able to be in that rejection region at the 1% level. So you can do this for multiple levels of alpha with the critical value approach. It's just, I don't know, I find the p-value approach a little bit easier because you just have this one value and you just quickly compare it to 0.1, 0.05, 0.01. Any questions on that idea? So using that last row of our T table, remember, is just the same as looking those values up in our C table. Okay. In fact, I think we'll stop here. So I think we'll save sample means where we only have sample variances for Monday. I'll probably go through a little bit quicker and then we'll kind of start doing some work in Excel. I might even start out with some work in Excel and we'll kind of transition to that. But I want to go through one more thing. I've got this Excel file up on Canvas, which is this HT example tuition. So hopefully this gives you a little bit more of an understanding behind what we're doing with hypothesis testing. Now, this example, well, we're taking a step back and I'm thinking about just one population examples to make it easier, okay? But I think hopefully, I don't know, for me, and you know, not everyone's gonna be like this, but for some of you, seeing something actually play out in the data as opposed to just hearing about it theoretically usually helps make a little bit more sense. So we go back and remember our one population examples. Right, we found our test statistic like this, right? So something like this. So what we're trying to do is, okay, look, if we take a sample, if what we assume to be true is in fact true, it should be the case that our sample means are normally distributed around that. So when I find a value that's out here and I turn it into a test statistic, and I figure out the probability that I saw that test statistic or anything more extreme, right? Let's say that p-value is 0.03, right? If what I assume to be true is in fact true, so whatever this value was, let's say 10 years down the road, I figure out that was exactly the right mean. Well, for any value that I see, here, what's a better way to do this here? We'll do, say I do the 5% significance level, right? For any value that was more than this many standard deviations away, I'm going to end up being in the rejection region or with a p-value that's lower than alpha, right? Lower than 0.05. So for every value here, I will end up rejecting the null. But if what I assumed was true was in fact true, I still could have seen those values. It was just a really low likelihood. So essentially, for all of these values, I'll be rejecting the null when I shouldn't be, right? Which is what we said is a type 1 error. This is why we can't say it with 100% confidence. Because even if what we assume to be true is in fact true, if we set alpha 0.05, 5% of the time, we're going to see a sample mean somewhere in that range, and we're going to reject the null when we shouldn't be. Right? But 95% of the time, right, we'll be okay. Right? So let's think about if we had some data here. I think I had different schools, right, different universities, and what their tuition amount, or at least reported tuition amount was. So data's a little bit old, so this is probably a little bit low, but you have to remember, also have to remember this includes like really small, even some community colleges are in this data set. So we've got this true average tuition of about 13,000, right? And I believe all these were reported in-state tuition, so that makes a little more sense as well. So I know what the true population mean is, right? I know this true population mean 13,000, right? I also know what that true population variance is, right? So I've got this known population variance. What I'm then going to do is say, okay, look, I can kind of cheat because I know the population data. I'm going to just start taking multiple samples, right? So I'm going to take a sample, right, of 50 different universities, find the sample mean tuition for those 50 universities, turn that into a test statistic, right, where I'm assuming that the true difference is in fact that true mean. So like I'm kind of cheating here in that I know my assumed true value is right, right? But it helps kind of prove the point that if what we assume is in fact true, what proportion of the time are we still going to be making these type 1 errors? Are we going to be rejecting when we shouldn't be? So I can cheat. I don't have to just pull a assumed true value out of there. I know what it is. So if I'm using the actual mean as my kind of assumed true mean, so I'll go down here. Whoops. I've got these, and you can kind of ignore this first column. This generates some like random numbers that it then kind of uses to look up different random universities. You don't have to worry about doing that. I'm not going to expect you to do that. All I'm doing is calculating the sample mean from that first sample of 50 schools, and then kind of finding that sample variance, right? And then turning it into a test statistic. So all I'm doing there is taking the sample mean I found, subtracting this assumed true mean, which we know is in fact true now because we had the population data, and then dividing by kind of my population, my known population variance divided by my sample size. I just use the count function here. I could have probably done this in a different cell. Once I have that test statistic, how can I find my p-value? Well, if I've got this test statistic, I can find the area. Sorry, let me redraw this. Once I have this test statistic, I can find the area in my tail. And if I have a two-tailed test, I then need to multiply that by 2 to get my p-value. So that's all I've done here, right? I've taken that test statistic, I looked it up in that Z table, found the area in the tail, then subtracted it from 1, right? Finding the area in the upper right tail, and then multiply it by 2. I did some other goofy stuff here, just to make sure that if it was a negative value, the way that I have this coded, I would be finding the area in the left tail and then multiplying that by 2, right? So that's essentially why I took the absolute value, right? Just to make sure that it didn't matter if it was positive or negative. I'm finding the area in that one tail and then multiplying it by 2. Okay? I then said, okay, look, I'm going to use this if statement, which we've kind of used a little bit to see, do we reject or we fail to reject, right? I showed you how to do this in one population where if the p-value is less than alpha, so if this p-value, the previous cell is less than alpha, which I have somewhere way up at the top, I can show you in a second, put a 1. That means I am rejecting. If it's not true, well, then I should be failing to rejecting, put a 0. Okay. So if we go up here, I've got alpha set at, oh, where is it? There it is, 0.1, right? So I should be making errors 10% of the time, right? Because I know what I assume to be true is in fact my true value now. Okay. So I come down here. Oops, going a little bit too crazy there. There we go. And I said, okay, look, for each one of these different random samples of 50, I have whether or not I rejected null or not. So all I'm going to do is count the number or add these up, which should give me the number of rejections I'm making. So I'm out of these 1,000 random samples, I'm making 106 rejections. So I can think about, well, what's the proportion of rejections I'm making? It's going to be that divided by, well, I took 1,000 samples. Of those 1,000 samples, 99 of them I rejected the null. I generate more random numbers. I've rejected 106 or 0.106 proportion of them. I can kind of keep going through this. And what I see is this number is hovering right around, excuse me, that alpha value I set, right? So I'm going to prove this to myself by taking these random samples that, yeah, even if what I assume to be true is in fact the true mean, right? So this assumed true mean that we're using, it was in fact exactly the true mean. We would still be making errors, kind of whatever that alpha threshold level we set proportion of the time, right? Or if we want to turn that into a percentage, right, just multiply by 100 to kind of move that decimal. Now, if we play around with this, if I change my alpha to 0.01, when I go down here, the proportion of times I should be rejecting, even when I shouldn't have been, should now be 0.01. Well, I thought that would stay down there for me. Now it's a little off, right? It's just a little bit under 0.01. Now it's a little bit above. It's going to hover right around that because in theory, to actually get it to be exactly 0.01 or 0.1, we would need an infinite number of samples. We can't do that, right? But we can at least kind of prove to ourselves like it's pretty close, right? It's always going to be hovering around that alpha value. Okay. Any questions on this before we keep going here? Okay. So I think we'll leave it there, get out a little bit early today, but we'll pick up on this on Monday. We're going to then do examples where we have 2 sample means and we only know sample variances. It's going to be pretty much the same as what we did when we knew the population variance. We're just going to have to do the student t distribution. Okay. So we'll pick up on that, do some more Excel work on Monday. Other than that, I will see you guys. Have a fun, safe weekend, and I'll see you on Monday.